In Chapter 10, we deal with projectile motion and satellite motion. I'm going to split this into two videos. And with this first one, we're going to just look at projectile motion. A projectile is anything that's launched. When you think of projectiles, I think of things like footballs, baseballs, even rockets. But the important thing is, after it's launched, it follows a path that's determined entirely by gravity. The only force acting on a projectile is gravity. Now, what makes projectiles actually fairly easy to understand is that the horizontal motion and the vertical motion are completely independent. Let's think about just for a minute. I'm going to talk a lot more about this. Suppose that you've got a cannon up here. There's my cannon. And I barely fire it. I have a misfire. And it just falls just like free fall. I do it over again, and this time I shoot it faster. But when I shoot it faster, oddly enough, it's moving horizontally, but the falling part is exactly the same. So if this is at 0 seconds, 1 second, 2 seconds, the falling part is exactly like free fall. Really important to understand what's going on. Horizontally, remember, the only force is gravity. So horizontally, we have no force. So we have no acceleration. If I have no horizontal force, I have no acceleration. That means my horizontal velocity is constant, and the horizontal distance is going to, all right, that's a constant. It doesn't increase, it doesn't decrease. And the distance traveled horizontally, I usually use an X for horizontal distance, is just going to be the horizontal velocity times the time. That's that distance equals velocity times time, but now I'm using X for the distance. That's what happens horizontally. Vertically, it's just like free fall. Vertically, we know that we have an acceleration that is 10 meters per second squared, and that's downward. And we know that we have a vertical drop that's equal to 5t squared. That's the exact same formula that we had before. Okay. We also know, and I guess I could have written this down even before, that the change in velocity, how much the velocity increases, is going to be equal to that acceleration times the time. And of course, the distance that it drops, I'm going to call that y, is 5t squared. The important thing you need to understand is that the horizontal motion doesn't affect vertical motion, and vertical motion doesn't affect horizontal motion. We'll come back. There's really two different types of projectile problems. We're going to look at a horizontal projectile first. back to our cannon up here on our cliff. When we have a horizontal projectile, we're shooting things horizontally. But before I shoot one horizontally, I want us to just think about, if I drop it, it'll fall straight down. But if I shoot it horizontally, it'll travel a path that looks something like this. It looks like a parabola. It really looks like half parabola. If I shoot it a little faster, it'll look like this. If I shoot it even faster, it'll look like this. But when you look where the cannonball is, vertically, it doesn't change. When it's here, it's here, it's here. They're all falling. That part of the motion is exactly the same. What's different is the faster I shoot it, the farther it's going to travel horizontally. But shooting it faster horizontally doesn't affect how quickly it drops and it falls to the ground. If you were to say you shot it here and it took 4 seconds to hit the ground, shooting it faster, it still takes 4 seconds to hit the ground. In fact, it's interesting, if I drop a bullet, so I'm holding a little bullet right here, this little pin cap can be one, and I have a gun, and I fire the gun, and I drop the bullet at the same time, the bullet fired from the gun hits the ground at the same time the bullet that I dropped does. Now, that seems, a lot of people think that the one you fire should take longer. But if you think about it, it makes perfect sense. If you hold the gun pointing up a little bit, you know the one you drop will hit the ground first. If you shoot the gun down a little bit, you know the one you fire down will hit the ground first. So it only makes sense that if you fire it horizontally and you drop it horizontally, and you drop it, they should hit the ground at the exact same time. Let's look at an example. Let's put some numbers just so we can think about it. In the example, I said we have a cannonball launched at 7 meters per second. It's launched horizontally. At 7 meters per second and hits the ground in 5 seconds. We can pretty much know enough to figure everything we want to out about this problem. Let's draw the picture again. Here's the cliff. Here's the ground. There's my cannon. All right, a launch cannonball, when it leaves the cannon, it's going 7 meters per second horizontally. But remember, as soon as it leaves the cannon, it's also in free fall. So even though it started off with the vertical velocity of 0, 1 second later, it's falling at 10 meters per second. And 2 seconds later, it's falling. The downward velocity is increasing. It'll do something like this. Looks rather like a parabola. If I want to know where it landed, right here, I know that horizontally, it went 7 meters per second for 5 seconds. So it went 35 meters. That exit's going to land 35 meters away from the cliff. But I can ask some other questions. I can say, well, how fast was it falling when it hit the ground? How high was that cliff? Well, if I want to know how fast it's falling, I need to remember that vertical motion, that the acceleration is going to equal 10 times t. So if it's in the air for 5 seconds, when it hits the ground, it's going 50 meters per second. So right when it hit, not after it stopped, right before it hit, it's going 50 meters per second. Once it hits the ground, it stops. All that kinetic energy gets turned into thermal energy and gets dissipated. But we know this was its speed vertically when it hit the ground. Now, when it hit the ground, it had horizontal speed and vertical speed. When it hit the ground, it was going 7 meters per second sideways because that never changed. And it was going a whole lot faster and 50 meters per second straight down. If I really want to know how fast that is, I have to do the Pythagorean theorem. And I have to say 7 squared plus 50 squared equals the resulting speed squared. That's 2,500. That's 49. 2,549. The overall speed is probably going to be just a tiny bit faster than 50 because that's going to add a little bit to it. Let's see. The square root. It's going to hit the ground with a speed of about 50.5 meters per second. That's an interesting question because a lot of people, if you say how fast was it going when it hit the ground, they may think it's going the same speed as something that was dropped. But something that was dropped straight down would only have a speed of 50 meters per second. But since this has a horizontal and a vertical speed, both, it hits the ground with an overall speed of about a little bit over 50 meters per second, about 50.5. The other thing that we can answer about this is we can decide how tall the cliff had to be. How high is the cliff if it takes you 5 seconds to fall? Well, it's exactly like free fall. We know that the distance that something drops is 1/2 gt squared, or the distance that it drops is 5t squared. So if the time was 5, and we square that, that's going to be 25 times 5. It was a 125 meter high cliff. I'm going to put a little y there to remind you that's the vertical speed. 7 is the horizontal speed. But that's how a horizontal projectile works. If I increase that speed, say from 7 to, let's make it go 10, it's going to go farther. In fact, I can tell you how much farther. If I change that to 10 instead of 7 here, it would travel a distance of 50. It would still take the same exact amount of time to hit the ground. The amount of time it takes to hit the ground doesn't change when you fire it faster or fire it slower. The only thing the amount of time it takes to hit the ground depends on is how high was the cliff. The farther it has to fall. If it took 5 seconds to fall, it's going to be 125 meters high. All right, the other type of projectile is one that launches at an angle. If you have something like a football and you kick it, when you launch that football, you launch it at some angle, like this. If there was not any gravity, it would travel in a straight line forever. But because there is gravity, the vertical motion is going to be subject to change. Let's suppose it's going this way. I'm going to put some numbers here. Maybe Vx is 6 meters per second. but Vy is 8 meters per second. Well, if it's going 8 meters per second up, it's not going to be going up very long because 1 second later, it's already on its way back down at -2 meters per second. What happens with a projectile is it moves in a full parabola that looks like this. That's what happens if you draw a baseball. That's what happens if you kick a football. It will make a parabola. This path, that distance underneath is that 5t squared. That will tell you how far it has dropped off of its original straight line path compared to where it would have been. We know that horizontally, it's going to follow a straight line. This is only going to take about 0.8 seconds to reach, because I did really small numbers. This is only going to be up in the air about 1.5 seconds because I did use such small numbers. So if it's in the air for like 1.5 seconds, it's only going to go about 9 meters this way. It's going to go up and then back down. I don't think we're going to do very much with numbers here, but I want to make sure you understand what's going on. Horizontally, we go at a constant speed. This horizontal speed does not change. Vertically, we could just change this to some bigger numbers just so we can see. Let's make that be 40 and make this be 10. Well, after 1 second, this will still be 10, but this will have dropped to 30 meters per second. After 2 seconds, this will still be 10, and by that point it would have gone 20 meters this way, but this will be down to 20 meters. In fact, it will take 4 seconds to reach the top and 4 seconds to come back down. So I can tell the whole thing if I start off with 40 meters per second here. It's going to take about 8 seconds. 4 seconds going up, 4 seconds coming down. We could even make that table of values that we made before. If I wanted to make a table of values, let's look at the two velocities. I'm getting kind of sloppy here. At the very beginning, this is 10 meters per second. This is 40 meters per second. But if we wait 1 second, this doesn't change. Horizontal motion does not change. It's 10 meters per second horizontal the whole trip. Vertical motion, however, does, because we have an acceleration due to gravity that points down. And it's 10 meters per second squared. Well, if the motion goes up 40 meters per second, in 1 second, it's going to have dropped to 30, then 20, then 10. By 4 seconds, it's reached its maximum height. Another second later, now it's going -10. And all that means is now it's going down. Then -20, then -30, then -40. Notice it's symmetric. The time it takes to go up and the time it takes to fall back down are going to be exactly equal to one another. In this case, since it left going 40 meters per second, we can figure out, oh, it's going to hit the ground in 8 seconds. Where is it going to be? Well, if it's going 10 meters per second sideways for 8 seconds, it's going to travel a distance of 80 meters this way. I can even figure out how high it went. I know it takes 4 seconds to get from here all the way down to here. And I know that when something's in free fall, that's how far it drops. So if it takes 4 seconds to come down, it's going to drop 80 meters also. That was kind of an accident that I made the horizontal and vertical distances come out the same. Obviously, I didn't draw the picture to scale, but that's how it works when you're launched at an angle. Now, if you think about it, different angles are going to impact how far something travels. If you can totally eliminate air resistance, what you're going to find is you're going to get the best distance if you launch at 45 degrees. If you launch too high, you come down too quickly. If you launch too low, you also come down too quickly. Generally, you are going to, angles that add up to be 90 will land at the same spot. So 75 degrees and 15 degrees will actually cover the same distance, and it won't be that far. If you did 60 degrees and 30 degrees, you would see that also. Now 60 degrees may do something more like this, and 30 degrees may do something more like this. But they too don't go as far. You get that maximum distance at 45 degrees. Now, in real life, we cannot totally ignore air resistance. So in a lot of real life applications like baseball, you're going to go farther if you actually bat the ball at an angle that's less than 45 degrees, maybe closer to 40 degrees or 35. But if we could, because of the role that air resistance plays, but if air resistance is taken out of the picture, then 45 degrees is going to maximize your distance. Okay. One of the things I want you to be sure that you realize is that you understand what's going on as far as acceleration and velocity. When you have a projectile that does something like this, if you're right here, what's going on? Well, your velocity is that direction, and at that particular point, it's not rising or falling. The vertical velocity is 0 right there. But your acceleration is always down. Now, when you're over here, your velocity is this way. But your acceleration is always down. In fact, it's always negative 10 meters per second squared. In this case, we tend to think about the y velocity is up. Of course, the x velocity is still over. Notice the arrows always point towards the right. If you're over here, the velocity is in that general direction, but the acceleration is still down. No matter where we are on this path, whether the ball is rising or whether the ball is falling, the acceleration points down. Notice on the way up, when velocity and acceleration point in opposite directions, it's slowing down on the way up. When it's falling and acceleration and velocity point in the same direction, you know it's going to speed up. The other thing I think I've already talked about that I want you to realize is the time it takes to go from the ground to the very top. In this case, if we fired it upward at 40, it's the same as the time it takes to go from the very top to the very bottom. It's symmetric. It's going equally fast both places. However fast it's launched, that's how fast it's going to hit. Now the direction will be different, but it will have the exact same speed. Okay, I think that's everything I needed to share about horizontal and vertical projectiles. The next video, I'm going to make one more short video for this chapter, and we're going to talk about satellite motion.